iPhones, smartwatches, the latest laptops. Let's face it, our appetite for electronics is not slowing down anytime soon. And what comes with that is an increase in e-waste. I'm Shini Somara here in Switzerland to meet some scientists who are working on some eco-friendly solutions derived from wood, which when disposed of won't contaminate the environment. And this is all better known as green electronics. Electronics are a mixture of plastics and metals, none of which is biodegradable. A recent UN report found that globally, we're throwing away 48.5 million tonnes of electronics, 80% of which ends up in landfill. Here at EMPA, the Swiss Federal Laboratories for Material Science and Technology, scientists have developed a material that can replace all that plastic, and it's all made from wood. Dr Gilberto Siqueira is the lead scientist.
The three main components of wood is cellulose, lignin, and hemicellulose. We start with the bulk wood. We cut it to small pieces, shaped like this.
So you're almost shredding the wood down to paper-thin strips?
Yeah, the smallest you have in the beginning, the easiest for the fibrillation. After this process, what we have is a chemical process, which is well established in the industry, where we produce such kind of wood pulp. Here is the dried wood pulp. You can see this fiber-like structure that we have.
It's like dried paper mache.
Exactly. But here you only have cellulose.
Okay. And why is cellulose so important?
Cellulose is very interesting due to its mechanical properties. It's easy to functionalize. We can use it for many applications in our daily life.
Cellulose is a long-chain molecule known as a polymer, which is made up of repeating chains of a smaller molecule. It's made of glucose, which in turn is made of carbon, hydrogen, and oxygen. Cellulose is the main substance in the walls of plant cells, helping them to remain rigid. Why is cellulose the most important part?
Printing electronics, we use nanocellulose in the composition of the ink that we prepare for 3D printing.
To make that ink, more water is added to the tissue paper, turning it into a cloudy fibrous liquid. What's happening here?
So basically,
Gosh, look at the size of it.
This is the machine that we use to grind the cellulose fibers.
So what exactly is in the machine?
So inside this machine, we have two grinding stones, such as this one here. So those stones will be in close contact to ground the cellulose fibers down to the nanoscale.
Can we see that?
Yes. So we have here a solution of cellulose fibers in water, 2% of cellulose, and the rest is water, 98% of water. So very liquid-like.
It's like glue.
Yeah.
What's amazing is that it doesn't seem like a material that needs grinding because it's liquid.
It's suspension, I would say, of fibers in water.
The cloudy solution, getting splashed. The cloudy solution that's in this big bowl is being sucked into this machine here, and two stones that are very close to each other are responsible for grinding this solution into an even finer solution. But as it goes through the process of being ground down, those fibers are going to become so small on a nano scale that actually this liquid is going to become clear.
Just come into the lab. So I'm going to show you here two components that we use to prepare our ink. So in this morning, we saw the preparation of cellulose nanofibers, which is a kind of a gel-like material.
So that's the end result of that mechanical process?
Something like this.
So this is your 3D printing ink?
Yes, this is a material that we will put in a cartridge and 3D print.
Oh, 3D printer.
Yes, so in this printer, the material will be driven by pressure.
So it's finally possible to 3D print materials that have similar properties to plastic, but are entirely biodegradable. But how much impact will it have on electronic waste? I just got to We Charity near Manchester, where a lot of old electronics gets collected up from various locations and dumped and sorted right here. Hi Mark.
Hi, how are you?
Gosh, this place is packed.
It is, it's just full. Even including this room here, it's just full of IT equipment, DVD players, monitors.
We Charity specialises in recycling, refurbishing and disposing of waste electronics. Volunteers dismantle and restore 70% of the waste they receive. They recover significant quantities of precious metals, but electronics also contain toxic substances, such as mercury and flame retardants. If it wasn't for the work they're doing here, it would end up in landfill, ultimately harming our environment. So what proportion of the electronic waste that we discard is actually recycled?
I would like to say 100%, but I can't always say 100%, because obviously some plastics which are contained within these components can't always be recycled. So there is some element where some of it may end up in landfill.
Like the actual motherboard, how much of that is plastic?
It's really difficult to tell because you've got components here, these are all plastic. Yeah. So as an estimate, I'll probably say about 30%.
So about 30% of this component can't be recycled because plastic?
It can't be yet, but that's not to say that we can't find a way in the future to do that.
So much of our electronic waste ends up in landfill, and so precious metals like this gold dust is lost forever. But thanks to the research being done in Zurich, that may not be a problem in our future.
If we want that material becomes conductive, then we can also add conductive material such as silver nanowires, silver nanoparticles, graphene. It really depends on the final properties, what you want.
So at this stage, it is not conducting?
Not yet. Only if you add a conductive material.
It also has components.
Gustav Nystrom is the head of the science department at EMPA. So what are the applications of this technology?
So I think it's really interesting for instance, thinking about sensing, environmental sensing, placing sensors into nature or agriculture where they can take up signals, measure things, and if they are left there, they are creating no side effects or no harm. It's also interesting to think about something like packaging, where we want to maybe try to create intelligent packaging materials where you couple sensors or energy storage devices that can monitor whatever is inside the package. And for instance, determine if it has passed certain levels of humidity or heat, or if it's stored under such condition that it is in good shape. Thinking about medicine, vaccines, these kind of goods, I think is very interesting.
Those sensors might look something like this. Thanks for watching. Don't forget to like, comment and subscribe, and hit the bell button below for notifications.